I'll just give a quick introduction. Sadly, Bernhard's flight got cancelled yesterday, so we have him here remotely, and with that, I will give the word to you, Bernhard.
Thank you so much. Okay, so let's quickly check if you guys can see my slides as well. At least they should be visible, right? Let's see. There we go. Now it should be fine, yes?
Yes, we see.
Awesome. Okay, great. Thank you. Okay, so then let's get started. Just 1 second. Here we go. Perfect. All right. So, yeah, so everybody welcome, and thank you so much for joining for this part of the course where we talk about rendering and geometry from 3D Gaussian splatting as part of the symposium on geometry processing. And we're going to do this because 3D Gaussian splatting has become not only a way for rendering things from images really, really quickly, but actually also for geometry extraction. So it's become a method for recreating 3D representations from 2D images. And then, of course, you can, from that 3D representation, extract some sort of geometry. We're going to cover this part, the one about geometry processing, a little bit later. So we're going to structure it like this. The whole course, all in all, will be approximately 90 minutes. And I myself will be doing an introduction to 3D Gaussian splatting, what it is in general. We will hear about artifacts that can occur in the 3D Gaussian splatting representation and how you can potentially address them. And then there will be an overview about methods for actually extracting geometry and how well they work or don't work, and what there is still that needs to be fixed, and what you might be able to fix yourself in your own work and make things better for 3D Gaussian splatting for geometry. So first up, what is 3D Gaussian splatting? So 3D Gaussian splatting was developed as a method for novel view synthesis. So what does that mean? It basically means that if you have images of a certain object, like for instance, this tree stump in this scene right here, from these individual images, you can create new renderings from views that were not there in the set that you used to train. So basically, let's say you have, for instance, 30 images of this tree stump, and you are, after the process is done, able to generate new views from which you didn't photograph that object, right? So that makes it really interesting if you have something where you don't know ahead of time the specific angles or viewing directions from which you might want to shoot something, let's say, for instance, for movie production or something similar. And this is where this really comes in very handy. Now, this already was possible before. So there were methods for doing these kinds of things, like, for instance, with NURBS, with methods from photogrammetry. But we were basically targeting an approach that actually can achieve real-time rendering, where you can, in real time, move through these reconstructed scenes and basically have no delay between your novel views. So you basically, like a first-person shooter, can move through the scene freely, and you get your novel views delivered at 100 frames per second or more. And we were also going for high-quality renderings. So we basically wanted to obtain really, really good accuracy to the images that it was being trained on. Also, we wanted it to be fast and easy to obtain, and we wanted the representation to be reasonably compact. So all of this basically led us to the development of 3D Gaussian splatting. Now, how does 3D Gaussian splatting work in general? You start from structure from motion points. And if you're a little familiar with how camera calibration registration usually works, you might know that usually what happens is when you find out where cameras are in space, where unposed cameras are in space, you basically need to find matching points in the images that each of them have captured. And then you figure out with trigonometry and all kinds of nice tricks how the cameras are most likely oriented and aligned relative to each other. And these feature points that you use for doing that, basically in 3D, are usually what we call motion or structure from motion points. So basically the method for doing this is structure from motion. And these structure from motion, or SFM points, usually fall out of this calibration process, which is a very nice byproduct of a step that you usually have to do anyway. because you need to figure out, first of all, where your cameras are. And as a side product, you basically get those structure for motion or SFM points. And what we use in 3D Gaussian splatting is we start from these structure from motion points. We use them as an initialization. And then these points are turned into 3D Gaussians, which have a 3D extent in space. And those 3D Gaussians, which you can think of as like a blob or maybe a snowball, they basically get thrown onto the screen where they stick and split against the display and create a sort of soft color on them. And when you throw enough of these Gaussians at the screen, basically you will end up with very realistic imagery. So the training process overall, if we start from these Gaussians, let's say we have a poor initialization and we don't know where they're actually supposed to be, looks something like we just saw. You might start from a cloud of Gaussians, and then over time, these Gaussians move around and they change their color and they change their extent and they change their orientation. And basically all of these good things, some of them go away. And in the end, we end up with a reconstruction of the object in 3 dimensions. And of that object, we can then afterwards produce novel views. So there's a part in there that we didn't mention yet, and that we just actually saw in the video, but I didn't highlight it, and that is densification. So when you start out with those SFM points, and you only use those SFM points for the optimization, you end up with something that does not look photorealistic. Like for instance, in this instance here, you're basically limited by the number of initial SFM points that was generated in any one place. And that might often not be enough to get you something like photorealistic quality. So the cure basically to this is you increase the number of Gaussians whenever you consider it necessary. And our way for doing this is by using high positional gradients to mark those demanding regions, and we increase the density of Gaussians there. And the underlying intuition is that wherever you have a large positional gradient or XYZ gradient, you basically have a discontinuity detector in 3D, and you densify those regions incrementally by throwing more Gaussians there. So what's the idea here behind the positional gradient? It's usually caused by discontinuities in the current rendering with the target image or in the actual target image. So what does that basically mean? You might have this particular target shape that you want to match, and your current reconstruction looks something like this. And in this case, you will have high positional gradients at the borders of the Gaussians where the mismatch occurs, basically where the discontinuity between your reconstruction and the target is. So these Gaussians will be wanting to move to fill in the places where there's actually still Gaussians missing. So that's a good location for actually putting more Gaussians there, because the ones that are already there want to move because they want to fill in missing space. And the other thing is that if you are at the border, at the sharp border or the clear continuous silhouettes of an object, usually you also want more Gaussians there, because that's also, again, where you get a high positional gradient. And it's usually really important to get the contours of an object correct, or to get the silhouettes of an object correct, because that is usually where you want the most geometric versatility or flexibility to model actually the outlines of an object. On flat surfaces, it's not that important, but wherever you have like outline or silhouette detail, like fine detail at the borders of an object, that is where you want to have a lot of geometric flexibility to model its outline correctly. So again, it makes sense to put Gaussians in these locations. And the weaknesses of this very simple heuristic is that the densification, unfortunately, occurs often in areas that are already somewhat dense. And the final model size is effectively uncontrollable. So you probably will end up with something that is larger or has more Gaussians than it actually needs to have. So what's the current state of the art that we can talk about in 3D Gaussian splatting? So I'm not gonna start with the paper itself, because at this point, the original paper is already old news. I'm gonna jump into something that is, let's say, somewhat recent, and that also, as far as I'm concerned, in terms of 3D Gaussian splatting, is still pretty much state of the art. And that is treating 3D Gaussian splatting as a Markov chain Monte Carlo process. And that was produced by a very capable group including Shakiba Keratman, Adnan Salyashachi, and Kwangmu Yi, from various very high impact research facilities. And they basically modeled this whole densification process, not as just this simple heuristic, but by basically following the Markov chain Monte Carlo process and putting new Gaussians in the place where they have the highest likelihood of actually being required or being needed. And coincidentally, also, this Markov chain Monte Carlo process results to date in the, I would say, most robust, most established, high quality splatting-based reconstructions. So whenever you see the 3D Gaussian splatting techniques, the Markov chain Monte Carlo one is the one that very reliably and very robustly produces really high quality results. I would say in terms of 3D Gaussian splatting, it's the state-of-the-art flavor of doing it right now. So I would refer anybody to this particular method of doing 3D Gaussian splatting today for high quality reconstructions. Now, where are 3D Gaussian splats useful when you get them in high quality? So for instance, what you can do instead of just reconstructing still scenes, you can simply extend by a fourth dimension and have Gaussians that also move through space. You can have something that's called 4D Gaussian splatting, and that is now also its own individual domain of research. You can use them for inverse rendering and lighting. You can have Gaussians that have these physical material components, and to try to infer what those components are. What is their glossiness? What is their hardness? What is their reflectance of different lighting coefficients and different lighting frequencies? And so then afterwards, you have not only these Gaussians with a certain color, but something that you can actually relight and move lights throughout your scene, and for instance, integrate them into a gaming engine. Now, it's also become very popular as a method for producing generative 3D AI content. I will talk a little bit more about that in a while. It's also further applications down the road. There's a lot, and this is the most important one for the geometry crowd, surface reconstruction, of course. But also we have the ability to do fast structure for motion and multi-view stereo with the Gaussians and matching Gaussians that we assume are placed in individual images at particular locations. We can do collision and physics simulations in scenes that we only see from photos. And this is interesting, for instance, in domains like robotics. And we can have also human avatars. And this is where 3D Gaussian splatting actually is really impactful, because it has a really, really nice property of modeling 3D, of modeling human properties or human elements, like for instance, hairs and wrinkles and fine skin details really, really well. So it's become pretty much a weapon of choice for doing human avatars. So there was actually a whole session on just human avatars with 3D Gaussian splatting at the last SIGGRAPH Asia conference. So it's really, really impactful in there. Now, the question is, 3D Gaussian splatting, can we actually do it in setups that are non-researchy, that are very much applied, and that maybe don't even have that much of a strong hardware support? And the answer is very much yes. So 3D Gaussian splatting, basically the entire rendering process that you need once you have the primitives is just alpha blending. So if you know where your 3D Gaussians are in space, basically all that you need is a simple standard graphics pipeline that includes, for instance, a vertex shader, a geometry shader that turns the Gaussians into quads, then a fragment shader that evaluates the Gaussian function on this quad, and then finally you do some alpha blending together and you get the rendered scene. So the 3D Gaussian splatting representation is really, really quite portable and lends itself to almost any graphics pipeline out there. So it's actually really easy to implement into your custom engine, for instance. Now, the problem with 3D Gaussian splatting initially is their size. So the 3D Gaussian splatting solution is fast and it's portable, but its speed, if you, for instance, consider a distributed setting or something where you are online and you want to fetch some content, let's say you want to preview a product that you are maybe in the mood of buying and you want to download the 3D Gaussian splatting scene for this product so you can view it, that's going to cost you, because the original approach just produces a simple ply 3D representation. And this is usually in the order of 100 megabytes or sometimes even gigabytes. And this makes it quite unwieldy. Now, of course, there's another whole domain of research on taking the original 3D Gaussian splatting representation and then shrinking it down. There's by now, I think, a couple dozen papers on this particular topic on its own. We're going to go ahead and quickly give you an overview of our approach to this. So first of all, the memory cost of the original 3D Gaussian splatting models is quite high because it takes actually 59 times 4 bytes to represent a single Gaussian. And then in the end, as I said, with this simple densification approach and even the more advanced ones, you usually end up with millions of Gaussians for the full scene that you want to represent. And as we can see here, for some illustration, each of these many ellipsoids that we see here in the center images on the right-hand side, each of them basically requires 59 times 4 bytes to represent. And those go into position, rotation, scaling, the color, some view-dependent effects. So it's quite expensive per primitive. Now, representative of all the compression efforts that have been going on, here's a simple 3-step Gaussian compression that we have proposed. And one is where during training, you actually regularly prune the Gaussians that you have in your scene. So as you keep optimizing the scene, you regularly compute for each individual Gaussian a redundancy score. You threshold against a chosen threshold, and all those Gaussians that appear as if they are not contributing that much to the image quality or to the overall local density information, they are basically being pruned, so removed from the representation. A second step is to actually do the SH or the spherical harmonics assignment very adaptively. So what are spherical harmonics? Spherical harmonics are the representation of 3D Gaussian splatting to do view-dependent effects. So something like glistening or highlights that are direction-dependent. So for instance, a shiny surface. Those require those spherical harmonics. And we can basically choose to only place them adaptively. So in the original representation, every Gaussian in the scene would have the full capability to model any kind of view-dependent effect. And that is usually quite overkill because not every object in the scene is usually that highly reflective or that has that high frequency view-dependent effects. So what actually makes a lot more sense is to go ahead and pick those Gaussians that actually need that capability to model view-dependent effects and those that don't. And then we can go ahead and just assign spherical harmonics coefficients up to a certain band to those Gaussians that are rather diffuse, and then use more bands for those Gaussians that are really highly specular and have a lot of reflective components. And the last step that we use is code booking, where once we have done these optimizations, we basically localize clusters in the range of values that we actually use for the individual components of each Gaussian. So for instance, the rotation, the scaling, and the opacity, and the color, those usually cluster together around a limited number of interesting points. And everything outside of those interesting points usually is not really required that much. So we can sort of pick and choose certain feature locations and use those, let's say 256 feature locations, for which we have then stored particular values. And then, for instance, every opacity value or every scaling value can take on one of these particularly interesting 256 values exactly in the floating point representation. And that allows us to reduce the number of values stored with this kind of code booking, getting us very close to something like a 30 times compression overall. Now, here is a demonstration of what this looks like if you, for instance, use it on your mobile device. And of course, the side benefit of the smaller size is if you are, for instance, in a mobile setting, higher download speed of the scene. On the left-hand side, we see it in real time, the same scene being loaded, for which the other side struggles. And then again, with a smaller scene, of course, comes the benefit of faster rendering, significantly faster rendering in this case, which allows for better interactivity and usability overall. Now, we are going to bring these components together in a setting where we use them for virtual reality. And actually, we will hear a little bit more about that in detail later. I'm just quickly going to showcase how these benefits or how these changes to the original 3D Gaussian splatting representation come together. But if we combine a set of techniques that were built on top of 3D Gaussian splatting, it also becomes possible to go to a really nice VR ready representation. So for instance, the original representation has the problems of very, very large Gaussians that also deform strongly when you use a large field of view. And we see this a lot, and we see this particularly in VR applications. We see all of these very large Gaussians that are moving all over the place, that are popping in and out of sight, and that are basically covering much more than they should. And if we are careful, and if we apply some of these methods that actually we're going to hear about in a few minutes, we can actually get to a really, really solid representation that has none of these issues. So we can use the portability, the easy rendering that I just described of the 3D Gaussian splats, and some additional careful methodology to actually make them not only portable to any particular rendering engine, but even to VR applications, which is really quite nice. So I'm going to also talk about scaling it up, because 3D Gaussian splatting does not end at the scene level or at individual little objects. Because what we can see here is actually applied through all of the campus where we developed the 3D Gaussian splatting method, which is the INRIA Université Côte d'Azur campus in Nice. And we can actually see that we can go through the entire domain, the entire groundswork of this campus, and the 3D Gaussian splatting representation can model it all. And we can even run it on one machine. And actually, and I have to mention this, this scene does not use any kind of compression. So it's still using the old, very, let's say, wasteful representation, but still somehow we are able to store and fetch and render the entire INRIA campus on one single machine. Now, how is this possible? This is possible by introducing level of detail mechanisms. And we did this with a hierarchical 3D Gaussian representation, which we presented at SIGGRAPH last year, where we basically take a larger domain, something like this campus, we split it up into smaller manageable sections. And then for each of these manageable sections, we compute a hierarchical representation that allows us to stream only the amount of detail that we need for the current viewing position, and then render it with that amount of detail at 30 FPS or more. So in order to do this, we need to solve three questions. And one is level of detail generation. So first of all, for, let's say, 2 Gaussians that we have, we need to compute a level of detail representation that represents them both adequately from a further view or from a scene from far away. We need to, at runtime, select the correct Gaussian for the current detail that we need for the viewer. And then we also need to smoothly switch them out, so that when you take one Gaussian that is at the coarser level and replace it with its 2 children, the change isn't so sudden that it creates a disruptive effect. So the formulae for those who are interested are placed here on the slides. So the new position of the merged Gaussians are simply a weighted average of the children for the intermediate Gaussian. And the covariance is derived actually from a well-known formula that minimizes the Kalbeck-Leibler distance between the covariance Gaussian of the merged parent and its 2 children individually. So that has been derived actually by previous work in the graphics community. I think the last one was by Wenzel Jakob, who confirmed that this is the derivation for the best covariance to match with 1 Gaussian, the 2 child Gaussians to represent. Okay, now, what does this level of detail selection look like? So the level of detail selection at runtime basically is done based on the projected size of each individual Gaussian in the tree. So basically, you can think of the hierarchical representation as a simple tree, and then the set of Gaussians that is rendered is picked by picking or making a cut through the tree, with each Gaussian in the cut being picked as the last Gaussian that is large enough to basically cover a certain amount of pixels. So the first Gaussian in the tree as we descend, that for instance is no larger than 5 pixels, is the one that we choose for the cut, and then we don't descend any further. And that gives us a very simple heuristic and a very definitive heuristic for picking the cut of the tree. And that allows us to pick from the individual layers that we have exactly the set of Gaussians that we need for high fidelity to be visible on the screen. We also have then implemented a streaming render prototype that from this representation streams always exactly this particular cut of Gaussians from the tree onto the GPU. So with that method in place, we actually have no problem with running out of GPU RAM, because we will only ever have this subset of this particular cut that we are currently interested on there. So that is all very comfortable for us. Now, lastly, about the generation of 3D Gaussian splatting models, we also wanted to do something so that the original method, which was reasonably fast, was made still faster and still focus more on the details that we're actually interested in. So the original scene for something like the spike would train in about maybe 50 minutes total, but that is still sometimes prohibitively slow. So we came up with a method that actually is very careful about where to place Gaussians and places them in a very incremental, very tentative and very careful way. And with that, we can actually cut the time for training the models by more than 5 times. So this is called taming 3D.js. And taming 3D.js basically computes for the individual Gaussians scores that are obtained from the pixels that they correspond to within the images that we have, and how important those pixels are for conveying structural information. We also have a per Gaussian score that, in addition to the pixel score, takes some of the Gaussian properties, like for instance, the last gradient during training. And we also have some priorities for particular Gaussians with particular properties. For instance, those with a high opacity are the ones that we will be interested in more. And then we have a certain budget. And according to this budget and from the Gaussian score that we have, we will pick Gaussians that actually are more interesting to densify. And the interesting part about this method is that there is never any pruning in this methodology. So we never ever do any exploratory adding of Gaussians and then take them out. But we actually are really, really quite careful about where to initially place Gaussians ever. And that means we come up with a model and come up with a final model that is within a predefined budget. Let's say, for instance, 10,000 Gaussians or 100,000 Gaussians exactly. And we never ever basically reduce the number of Gaussians. So that means the memory consumption of the model consistently and strictly grows from start to finish. So there's never a spike in between or a peak in between for the model size that is later reduced or later is diminished again. And with that, we end up with something that trains both very quickly and very carefully and achieves with a low number of Gaussians, usually a very, very high quality. So basically an updated approach, which we presented last year at SIGGRAPH Asia to the overall 3D Gaussian splatting training methodology. Now, what else is there for 3D Gaussian splatting models? We are going incrementally and with each individual publication, we are going more and more towards lightning fast 3D Gaussian model generation and sometimes instant. And there's a few methods out there that are actually already very close to making very reasonable models with generative procedures and transformer procedures, where all you need, for instance, is use of some transformers plus attention to predict per pixel Gaussians from images. So we have a very pioneering work, which is Pixel Splat, which came out in 2024, which does this from sparse inputs and uses epipolar attention to then produce per pixel Gaussians for small setups of 2 cameras or 4 cameras instantly. We also have the method of using cross attention and only and exhaustive cross attention without any epipolar attention, which was used in GSLRM, which again, worked very well for small setups of 2 to 4 images and would basically produce in a forward methodology without any real optimization, merged Gaussians and very nice Gaussian models for small individual objects. And the recent extension to this line of work was the mixing of transformers and the lessons learned from Mamba in the space of large language models, which was called long LRM. And this basically takes a look at the quadratic complexity that makes the evaluation of tokens so painfully slow for attention. So they basically took the lessons from Mamba and found out that we can go with sub-exponential complexity, with sub-quadratic complexity, we can actually still achieve the evaluation of those tokens in pairs for the attention. And that allows them to go from these sparse inputs, 2 images or 4 images, to actually something like 32 or 64 inputs, which gives them the ability to make reconstructions of really entire scenes, for instance, at room scale, and again, instantly, like in the space of a few seconds or sometimes even less than a second, this reconstruction of Gaussians that we're seeing here. Okay. So I hope that gives you a decent overview of where 3D Gaussian splatting came from, where it is currently going, and what we can do with it right now. And I will now hand over to my very capable colleagues who will tell you more about the challenges. I was basically talking about all the nice properties that we have, but my colleagues will now be talking about the challenges and the artifacts that we can sometimes observe in 3D Gaussian splatting reconstructions, and also afterwards the opportunities that we have for actually extracting geometry from it, which will be the part that you guys will be most interested in. Okay, yeah, so thank you for your attention, and yeah, let's continue.
All right, thank you, Bernhard. Let's wait for the presentation. Awesome. So, now that you've gotten a nice overview about the current state of Gaussian splatting, I want to dive into more aspects of the actual rendering part and the artifacts that you can observe and that you have to deal with when you deal with Gaussian splatting and rendering. So, you might ask yourself, we have this beautiful Gaussian splatting scenes now, so why are we talking about artifacts in particular? Well, for example, have a look at this scene. And I want you to focus on the center of the table here. And as you may see, there's these weird popping artifacts that you can get when you rotate the camera. Or as Bernhard has already showed you earlier, trying to use Gaussian splatting for VR naively will suddenly produce something like this, where you have this weird large Gaussians that will distort into your camera. Or even just increasing the field of view may be enough to produce these distortion artifacts. So the goal of this part is basically to get an understanding of why these artifacts occur, explore different approaches from current state-of-the-art research works, and also just get a basic overview of what has been done in the last 2 years. So I want to start with the popping artifacts that you have seen in the first example. And to understand why we get these popping artifacts, we have to look again at the way that Gaussian splattings are actually blended, because as you may have already known, the Gaussians are transparent, which means that we need to do some alpha blending, and this is of course order dependent. So we have to sort them. And now the question is, how do we actually sort Gaussians? What do we take as step? And the easiest approach, and also what the original 3D Gaussian splatting does, is to simply sort the globally sort the view space depth of the mean of the Gaussian. However, this is exactly what results in these weird popping artifacts, as you can see here in this example, where if you rotate the camera, suddenly the projected mean onto the view ray of one Gaussian is nearer to the camera than the other one. And you can also see this nicely again here in this illustration. And what you can also see here is that the notion of projecting the mean onto the view ray does not really well correlate with the projected Gaussian onto the ray. So we have here this TU2 and the T1. And you can see that the T2 here does not really well correlate with the projected 1D Gaussian on the ray. And so a natural idea is to change this and also accommodate for the 1D projected Gaussian. And we can do this by basically just taking the mean of the 1D projected Gaussian and take the depth of this distance. And now we can see that rotating the camera does not really change the notion of depth, as this is now fixed to the Gaussian. However, we can also see that this is not an easy primitive as a plane. So basically, this is no longer a global way of sorting Gaussians, which means that we need to take a ray-based approach. And this is why we ask ourselves, why not simply sort the Gaussians for each pixel individually? And as you can see, however, we might have a lot of Gaussians to represent the scene, so up to a few thousand Gaussians per pixel. And while sorting per pixel does lead to no sort error anymore, if you look at the runtime, you can see that we are now more than 100 times slower. So this is obviously not really desirable. So this is where the well-known order-independent transparency methods come in. We can use basically approximations of the perfect sort order to make this a bit faster. So one of these methods is called k-buffers, which try to approximate the perfect sort order by using a fixed size buffer per pixel. So this avoids the memory overhead of a default A-buffers approach, where we would have basically a dynamic approach. And the way that this works is that if we have more Gaussians than size in our buffer, we simply blend the Gaussian with the smallest opacity and move on. And however, this approach does rely on an already nearly sorted list of Gaussians. However, as the default 3D Gaussian splitting already has this global sort schema, we can simply make use of this again and basically pre-sort the Gaussians globally and then try to resort them in these k-buffers. And one pretty natural idea is to maybe not do this per pixel to make it a bit faster, but to use a coarser grid across an image and basically make use of the already tile-based rasterization approach that 3D.js uses and simply sort the Gaussians per tile instead of per pixel. This should give a pretty good result because if you think about it, the depth of a Gaussian should be pretty similar across neighboring rays. So this should also mean that the sort order is similar. So we would get higher accuracy and avoid the per pixel sort. However, if you do this in a naive manner, you can see that we do get some weird artifacts across these tile borders. So still not what we really want. And this is where we can make use of a hierarchical sorting scheme. So basically the idea is to refine the sort order by introducing additional sorting layers. So if we have a tile here, we basically divide it into smaller tiles and smaller tiles and smaller tiles, and basically have a sort cube per individual sorting layer. I will not get too much into details here. As you can see, it is quite complex to do this efficiently on the GPU. However, what is important is that in the end, you can see that the error is drastically smaller than compared to default Gaussian splitting, while the performance is pretty much similar. If you're more interested into this topic, you can read the paper Stop the Pop by my colleagues Lukas Radl and Michael Steiner, also supervised by Bernhard. And now you can see that if you use something like this, the popping artifacts are basically gone. I want to mention that this is not the only approach. There are other approaches out there to solve these artifacts. One of them I want to mention is hybrid transparency, which basically wants to uses a much more simple scheme where they approximate the correct sort order by simply only sorting the first k Gaussians perfectly, and then simply blend the rest of the Gaussians into one color and blend that with the sorted Gaussians. So this is a basically a quality speed trade-off, as this cannot reproduce perfect per pixel sorting, but you can get a nice trade-off. And also they found that using only 16 Gaussians, so like sorting only the first 16 Gaussians, can be enough to achieve the same performance like 3D.js. All right, and with that I want to move on to the second type of artifacts I showed you in the beginning, these weird distortions we sometimes get. And to understand these, we have to look at the image processing of Gaussians again. So how do we actually get a 3D Gaussian onto the image plane? And if you remember, this is what a default Gaussian is defined as, and this is what a perspective projection for a pinhole camera looks like, where we have the focal length and basically the depth and the x and y. So I won't go too much into the math, but if we now want to basically project this Gaussian function, what we do is we take the integral along the ray, and if we plug in the perspective projection, you can see that in the end we get something out that is not a simple Gaussian anymore. And what this basically means is if we do this, you can see that the resulting picture is not a nice Gaussian. So this is not what we actually want, because we want a 2D Gaussian on our image screen. And this is basically also a bit intuitive that a Gaussian is not, does not retain its property under nonlinear transformation, such as perspective projection. So this is why we simply do a linear approximation, a local affine approximation, where we take the first order Taylor expansion of the perspective projection matrix, and we can then use this to project to get a 2D covariance matrix, which then defines our 2D Gaussian. The W here is simply a view transform. And if we do this, we finally get something that looks like a Gaussian again. However, of course, approximating something does introduce an error, and there has been a really nice work that dives into the analysis of this projection error. But basically, what you can see is that the error of projecting a Gaussian onto an image plane increases with basically on the border of the image. So the further out the Gaussian is, the more you have a distortion. And this effect is also increased by a higher field of view. They also propose a way to solve this issue. Basically what they do is instead of projecting onto only the image plane, they say we want to minimize the error. So what we do is we simply project the Gaussian onto a tangent plane of the unit sphere that is basically aligned with the Gaussian's mean. And then we transform this plane to the image plane of the camera, and this is how we avoid these distortions. And this is also what was done by the work that Bernhard mentioned earlier, VR split, where they use this to get rid of these high field of view distortion Gaussians. However, there's one drawback to this method, and that is that it introduces a lot more computational complexity. And therefore, there's also other approaches that try to solve these distortion artifacts by basically embracing the 3D nature of these Gaussians and directly evaluate the Gaussians in 3D, basically evaluating them along a ray instead of projecting them. And there has already been a plethora of papers on this topic, so I won't be able to cover everything here. But essentially, these can be divided into two approaches. And the first one is actually considering the volume of the Gaussian along the ray. So integrating the 3D Gaussian along the 1D ray. And this should basically result in the same thing that I showed you earlier with the shape that isn't really Gaussian anymore, because it does account for self-occlusion and also other things, and perfectly reconstructs what we see. However, the problem with that is that we have overlapping Gaussians. So Gaussians can overlap. And due to this overlap, it is not analytically possible to calculate the exact integral. So a lot of these works basically approximate or have some assumptions that make it easier to do so. There's this really nice paper that was supervised by Bernhard that dives deep into this topic, that actually asks itself the question if we need volumetric, accurate 3D Gaussian splatting. And I highly encourage you to read this if you're interested. A basic alternative to this volumetric approach is to do simple point sampling. So we basically sample only 1 point per Gaussian along the ray. This is way easier to implement and still avoids the projection error. The only question is, where do we actually sample the Gaussian along the ray? And similar to the depth approach I was talking about earlier, again, we can make use of the 1D projection of the Gaussian along the ray. So we have this 1D Gaussian, which basically is the projected 2D Gaussian, 3D Gaussian, and we simply take the point of the mean. So basically the projected mean on the ray. This also can be computed like this. Now, if you do it like this, you can see that this is what we had originally with the projection, and now with using 3D evaluation, you can see that these weird distortion artifacts are basically gone. So you might ask yourself, well, okay, we have solved both types of artifacts, we have no popping anymore, no distortion, so we are done, right? Well, not quite, because if you look at the video here, you may see that there's a lot of flickering going on suddenly. And this is due to our favorite type of artifacts, alias artifacts. And the thing is that 3D.js, with its 2D projection, actually has a bit of an advantage here over our 3D evaluation methods, because they have a 2D Gaussian on the screen, so on the image plane, and this makes it possible to simply use a screen space filter to ensure a minimum size of Gaussians. So the problem is, in 3D, we do not have that. And as we zoom out, the Gaussians become smaller and smaller, and we only sample along 1 point in a pixel, and therefore we get these weird aliasing artifacts. So in 3D, the anti-aliasing is not as easy as in 2D. This is where I want to talk about mid-splatting really quick, because they also have use a 2D screen space MIP filter, but they also have a 3D filter that was also used by a lot of works that relied on 3D evaluation of Gaussians. And basically the idea of this 3D filter is that during training time, we have all of these different views of a Gaussian from the different training images. So these are the camera positions of the training images. And what they do is they basically, for each Gaussian, find the camera that is closest during training. And they use the distance and the focal length to calculate the sampling frequency that this camera has for this Gaussian. And they then use this sampling frequency to basically define another low-pass Gaussian, which is then convolved with the original Gaussian. And basically what all of this does is it scales the covariance matrix of the original Gaussian, so making it bigger. Essentially as big as the pixel of this training camera, or at least as big as 1 pixel. And this ensures that at least one camera during training can reconstruct the Gaussian in rendering. And one drawback of this, of course, is as we do this with the training cameras, this filter is fixed after training. So this becomes an inherent part of the Gaussian. You can think of it as basically just scaling the Gaussian to a certain size during training. And with this, you can see that close-up it looks quite nice. However, if we do get further away, basically to the point where we are far away from any training view, we get aliasing artifacts again. So what can we do? Well, one basic idea is to simply use this 3D filter during rendering as well. So simply recompute the filter for each rendering view, so to say. However, if we do this, we suddenly notice that Gaussians seem to disappear or they are too transparent, let's say. And this is actually due to the normalization that this 3D filter uses. You can see it here. What this basically does is it ensures that the total volume of the Gaussian after scaling it up stays the same. So we do this because otherwise the gradient descent would simply make Gaussians at high frequency details smaller and smaller to a point where they are numerically very unstable. However, if we do point sampling in 3D, so we only consider one point along a ray, we do not consider the whole volume of the Gaussian. And therefore, regularizing it by the scaled volume basically makes them too transparent. It's an over-regularization. So the idea is to simply only consider the increasing extent of the Gaussian perpendicular to the view ray we have, to the pixel ray. So you can see that the volume here of this orange Gaussian, for example, almost doubles compared to the blue Gaussian. However, the extent on the actual screen is only minimal. So I won't bother you with the details, but essentially it comes down to a new regularization factor that, if you simplify this, comes down to a very, very simple calculation. And with this, we can get rid of these aliasing artifacts during rendering. However, this is not quite the whole story yet, because there's still one more problem. Because as we recompute the filter for each rendering view, if you zoom in, so basically if you go really close up to Gaussians at the point that you haven't seen during training, you suddenly notice that Gaussians become very small, way too small. And this is actually due to the fact that we have never seen them at this close-up scale during training. And how we can fix this is to, again, use the fixed 3D filter I talked about earlier from Gaussian Splatting to basically have a minimum size of this filter. So it basically bounds the filter. This results in a more blurry but accurate result from what we see during training. And here's a small comparison again. This is without any filter. This is with a 3D fixed filter only, so only the training filter. And this is with the total filter, the adaptive filter. So you can see that at any level, there's no aliasing anymore. Same with the close-up. This would be with the adaptive filter without the training filter, without the bounding, and this is with the bounding. So if you're more interested into this, you can read more about it in our paper, AAA Gaussians, which will also be presented at ICCV later this year. There's one more approach I want to mention, as there's, as usual, not only one approach to solve the issue. So another approach to get rid of aliasing artifacts, this is again 2D, I just want to mention this here quickly, is analytic splatting, because I find it quite interesting, where they actually try to sample the 2D Gaussian not only at a single point, but approximate the actual integral over the total pixel to solve the aliasing artifacts. And this does result in a more accurate representation. Of course, I haven't talked about every artifact yet. So there are a lot more artifacts that can occur, like floaters, holes, depth imprecisions. For example, a lot of times with Gaussian splatting, you can see that the sky gets really weirdly distorted because there's not much depth information that can be recovered, and also things like over-blurring of things, which all of them basically come down to having too less of information, for example, not enough images, training images, or simply not enough Gaussians for your training to represent the information. All right, and with that, I'm done with my part, and we'll give the word to Felix, who will talk about a bit more geometric-related stuff.
Thank you. So for the final part, we will be talking about how to extract surfaces from 3D.js, because as cool as 3D Gaussians generally are, sometimes you do just need to go back to triangles. Some of the reasons for this are, for example, that in general, the editing tool for meshes are just much more mature. We have an easier time animating triangles, and also especially computing relighting, because in Gaussian splatting, by default, the lighting is more or less static. And also, if you want to do things like collision detection, things with the geometry, physics simulations, etc. So, in this chapter, we will specifically talk about explicit methods of mesh extraction, which means we take a set of input images, generate a 3D Gaussian model, and then convert it to a surface. There is a separate parallel branch of research which is concerned with extracting meshes by simultaneously optimizing some sort of radiance field, like either a NeRF or a Gaussian splatting model, and a neural representation of the surface. We have already briefly heard about this already today. The main difference between these two approaches is that the explicit method in general are much faster, and if they have not quite caught up in accuracy yet, they sure are on the way to it. So that is why we will cover explicit methods for now. So this chapter is split into two parts. First of all, we will talk about how to train these 3D.js models to extract it. And then finally, we will talk about meshing. So for the remainder of this talk, I will be representing 3D Gaussians as ellipses. Of course, they are not. There is a normal distribution fall-off. Just keep that in mind. So let's talk about training. We've already seen training today, and the results really look quite realistic. It seems like the training has completely captured the scene's geometry, and there's really nothing we need to do here. Well, what happened here? Let's take a closer look. Once again, the culprit is this metal surface in our little table here, where we can see that actually the surface is not represented by any Gaussian density at all. In fact, it is a hole which is pretending to be a surface. And if we were to extract a mesh from this model here, we would just get a hole where we would actually see a surface in the model. So why can this happen? Well, if we talk about traditional mesh rendering, we have some sort of light transport. And that means that if the geometry of the scene is in some way off, then the renderings will be off as well, because we can see it from the light source. The difference is 3D Gaussian models are not exactly physically accurate. They are floating blobs of light. And that means they can produce some truly incredible optical illusions. So the main problem here is that the problem of optimizing 3D.js in general is under constraint. There are many different configurations of these Gaussians which can produce the exact same image from a particular view. So if we want to get more geometric accuracy here, we need to constrain the problem in some way. And we do this by changing the target loss function. So this is the loss function that standard 3D.js is trying to optimize. It consists of two parts. The first one is the structural similarity index loss, and the second one is the L1 loss, which is the difference between the rendered images and the ground truth. So all this loss is caring about is, do the rendered images look like the images that we got as input? It's only visual. So we would like to add some terms to this loss, which care about geometric accuracy. Now, there's an immediate problem with this, which is, of course, we are given ground truth images of the scene, but we don't have access to any ground truth geometry. This means that we have to rely on priors. Specifically, we're going to want to get Gaussian splatting away from volume rendering towards surface rendering. And because this is a prior and we are constraining the power of the optimizer, this will lead to a decrease in visual fidelity. In general, by increasing the losses, we will get slightly worse pictures, but better meshes. So let's have a look at some of the geometric losses that we could introduce. First off, depth distortion. Let's have a quick recap of the volume rendering process for 3D.js. So if we want to render a particular view, we can think of this as this volumetric point cloud in which we sample these rays, one for each pixel. And then for each pixel ray, we'll be blending all of the Gaussians that it intersects together, like in volume rendering. But, of course, in volume rendering, we would integrate all of this. This is not really computationally feasible, so this is approximated discretely. So instead of 1D Gaussians along the ray, we will approximate them as sorted impulses. The rendering process would then start basically with a transparent color. And then for the first Gaussian, we would mix a certain part, depending on its opacity, of its color into the pixel. And we will reduce the transmittance, which basically means how much color this pixel can still accept from Gaussians, because it will occlude, this orange Gaussian will occlude all of the other Gaussians that will come after it along the ray. And then we move on to the next Gaussian, we mix a little bit of blue into our pixel, we reduce the transmittance once again, and so on. And this alpha blending process gives us our final pixel color. But do note that with this approach, we can alpha blend any property that we want to, which we will also use. Also, at some point, the transmittance will reach an early stop threshold, at which point we'll no longer consider any Gaussians. So for example, if along the view ray we hit 2 surfaces, we only really consider the first surface because it will already reduce our transmission below the early stopping. So if we want to extract the surface from this, we need to know where the surface actually lies. And in this case, it could be anywhere from the first Gaussian up to the time we hit the early stop criterion. We just don't know. What we would really like is to get closer to standard surface rendering, where there's just a single hit point and the transmittance immediately reduces to 0. So we would like our Gaussians to stick closer together. And we will encourage the optimizer to stick them together by introducing the depth distortion loss. So we want to punish the optimizer essentially for putting Gaussians, which are very important for this pixel, which have large contribution. We call this the weight, here W1 and W2. And we want to punish him if these have a very large distance along the ray. So we will add to our loss the product of the weights of 2 consecutive Gaussians times the distance squared. We will do this for each consecutive pair of Gaussians along the ray to get the depth distortion loss. And when we introduce this to the optimizer, it will naturally minimize the distance between Gaussians, giving us a much clearer idea of where the surface at this particular point should lie. But the surface is still not entirely smooth. Basically, we can't really figure out which way it's pointing. So that is where we come to the normal consistency loss. The basic idea here is that if we have a traditional mesh and we extract depth information from a particular view, what we can do is from this depth information compute also normal information for every single pixel. And we can do this using the method of finite differences. Basically, the normal vector at each pixel is given by the y gradient of the depth image and then the cross product with the x gradient of our depth image. And if we sample correctly, this will be exact for surfaces. So we also want this property for our Gaussian models. But there's a problem, because if we have like this rendering from a 3D Gaussian scene, how do we even find the depth and the normal vector? What does depth and normal vector even mean for 3D Gaussians? And this is unfortunately not an entirely solved problem, and there's a lot of competing definitions floating out there. We will go through some of them. So when we're talking about finding the depth of a pixel, we are once again interested in where is the surface of the object that we are looking at. One possible answer to that is to alpha blend the depths essentially. So we take the weighted mean, weighted according to the contribution to the pixel color, of the distance of the Gaussians to the camera. Now, just like the normal mean in statistics, this is somewhat susceptible to outliers. But it depends on every single Gaussian along the ray, so we can propagate the gradients to all of them. Another possible interpretation is of course, the median depth, which is less susceptible to outliers. Basically, we take the position of the Gaussian where the transmittance first dips below 0.5. So where we have used up half of the color capacity of that pixel. Now this loss can only be propagated to the median Gaussian, once again here. And also we still have this problem that we have simplified this, where all of the Gaussians are discrete. So this means, in general, we overestimate the median depth consistently. Because if this were represented as an actual 1D Gaussian, then we would reach the 0.5 line earlier. So we have proposed to compute this exact median depth, which computes the process as normal, except for the median Gaussian, which will then be evaluated analytically and exactly. Now let's talk about what is the normal vector from a Gaussian. One possible interpretation of this is just the normal vector should point into the direction where the Gaussian is most flat. So wherever the minimal scale direction of this Gaussian is, that's where it should point, and we use the plus minus sign to point it towards the viewer. Another feasible interpretation is not that Gaussians should point where they are flat, but they should generally point outwards, because that's what the normal at the surface does. So this is the intersection plane normal, which is dependent on the viewer, but still also transformed with the scale of the Gaussian. Okay, so we can then blend all of these normals together using alpha blending to get a normal map for every single pixel. And now we can introduce our normal consistency loss here as the difference between the normals that we have extracted from the Gaussians and the finite difference approximation of the normals, which we can calculate from our depth image. Now, because 3D Gaussians are kind of volumetric, this will not be exact, and we can use this as a target for optimization. One other cool thing we can do, if we have access to normal and depth information, is we can do monocular supervision. Because we have these really cool neural networks now, we can just take any image and estimate depth maps and normal maps from them without any additional information, like, for example, DPD2 or Marigold or similar. And then we can construct a really simple loss to just say, well, the depth map of our Gaussian model or the normal map of our Gaussian model should be close to the thing that the neural network predicts, which has been trained on a huge data set of images. Now, the question is, does this actually help? The answer is a resounding sometimes. Okay. In general, it has also been shown that more anisotropic, more flat Gaussians tend to produce more accurate surfaces. There's numerous ways we can go about them. For example, 2D Gaussian splatting essentially removed an entire axis from the Gaussians, making them not volumetric blobs, but disks in space that can only be scaled along 2 axes and rotated arbitrarily. This, of course, forces the Gaussian to have a unique surface. Another possible approach is to just leave this up to the optimizer and just say we want to minimize at least one scale of the Gaussian so that it is flat in at least one direction. We have found what also works really well is to put a loss on the extent of the Gaussians. So we alpha blend the size of the 1D Gaussian along our array and just add this to our loss. And what this will force the optimizer to do is it will flatten the Gaussian along the particular direction that we are viewing them from. Okay. Finally, we can also introduce multi-view losses. The idea here is to use information gained from multi-view stereo methods. So with multi-view stereo, we can take 2 images of the same objects, which are taken from close-by positions, and we can find pixel correspondences. So we find pairs of pixels which represent the same point in space between the 2 images. So where previously, if we had an optimization step, we were only looking at one image and potentially its normal or depth information, we are now taking into consideration 2 or more at the same time. And if we have such a correspondence between 2 pixels, and we know that they show the same point in 3D space, it stands to reason that they should also have the same color. So we can introduce an additional photometric loss where pixels that correspond to each other should get the same color in rendering. And also, since we now know how to compute depth values, we can also check if the view rays here actually see the same point in 3D space. And we can add this additional geometric loss between these 2 corresponding pixels, which all of these losses in some combination or another generally lead to a model which has more accurate surfaces in it. And when we have trained such a model, we need to convert it to triangles. There's two dominant methods currently. The first one is quite old, from 1996, TSDF volume fusion. And the second one is Gaussian opacity fields, which is just last year and specifically constructed for use with 3D Gaussian. So 3D Gaussians represent the so-called radiance field. And we can think of this radiance field also as kind of a density field. And we already know how to mesh density fields. We can use marching cubes. The result will be very poor, however, as you can see here. And the reason is that we have not taken into consideration the camera poses that were used to train the model. Because initializing the same scene from different camera poses will produce massively different results. So if we want to get a really accurate mesh, we have to take them into consideration. For example, using truncated signed distance volume fusion. What TSDF fusion does is it takes a set of post-depth images and converts them to a mesh. And we can get a set of post-depth images from our 3D Gaussian model using the mean or median depth we have discussed before. Importantly, the actual Gaussian information is not required for TSDF fusion. It has this depth map step in between. So think of this as a bird's eye view of this building here, and we want to reconstruct it. We have a post-depth map here, which essentially we can convert each pixel with its depth into a point in 3D space, which will give us one possible approximation of one patch of the surface of this object. And if we have a second post-depth map, it will give us a different approximation of a potentially overlapping patch of the surface of this object. Now, these are not going to be perfectly accurate for each depth map, so there is going to be some uncertainty. The idea of TSDF fusion is then that the true answer probably lies somewhere in the middle of all of these uncertainties. And we can represent this using signed distance functions. So, for example, for the blue approximation, we can get a SDF value for every single point in 3D space, which gives its distance to the closest point on the blue approximated surface. So in this case, the blue region here is inside of the object, and the red region is considered to be outside of it. We get a separate signed distance field for every single depth map that we have, which of course, that's too much data. So we need to fuse them all together. But first of all, we have to consider that these signed distance functions are only really going to be accurate in a very narrow band around the surface we are trying to reconstruct. So we truncate the signed distance function to a small interval, and then we do the fusion. So we can sample the fused SDF at a certain point by taking the average of all of the signed distance functions which are defined. So for this point, for example, the blue approximation would say it is outside of the object, giving it a positive value. The orange approximation would say it is inside the object, giving it a negative value. If we take the average of that, we would get something close to 0, which would mean this is on the actual surface of the object we are trying to reconstruct. In order to get the entire surface, we would then sample all of these truncated signed distance functions in a dense voxel grid, where we can then take the averages over all of them and classify them, for example, here into inside points in dark blue, outside points in light blue, and then also the 0 level set that we are trying to reconstruct in green. We can then, on this fused SDF, use a marching cube algorithm to get a more close approximation to the surface than any of the different depth approximations that we started with. So now, instead of just neatly using marching cubes on the 3D.js model, we have taken into account our camera views and get a better surface. But there is still a problem, which is that TSDF is very memory intensive. It is in general very fast, because averages are very fast, and so is marching cubes. But if you want to scale this up to large scenes, of course, your voxel resolution is going to suffer. So what you can see here in the left is that if you use TSDF, your background objects are not going to be reconstructed very well, if at all. So we need something else, like Gaussian opacity fields here. So to understand it, we need to go back to volume rendering this time exact with 1D Gaussians, which once again we remember we cannot integrate this to find the pixel color. But we can define the opacity along a certain view ray as just being the inverse of the transmittance. And if we choose some key assumptions, which is that the Gaussians never occlude themselves, they have no contributions after their mean, so we basically only take the first half of the Gaussian into consideration, and we accept some errors in the blending order, then what we can do is sample, this green opacity field function at particular points along the ray. So we take one point along the ray and we ask what is this opacity function. Then for all of the Gaussians that are closer to the camera, their contribution has already been made to the pixel, so we can represent them just as impulses. And for all of them that haven't been blended together yet, we can sample their 1D Gaussian distribution exactly at this point along the ray, and then blend them in our sorting order that we got. And this will give us an exact opacity along the ray. In a sense, an approximation of the real transmittance function. So let's see an example of how we can use this to extract a mesh. We have here our table scene. And if we want to extract a mesh from this, what we would like to do is to separate the inside of the object from the outside of the object and then find the boundary. So how we can do this is we define the Gaussian opacity field. It's the minimum over all possible training views of the opacity along its view ray to our sample point for every view. So for example, this left view here has no obstruction to our sample point, so it sees with an opacity of 0. The right view, however, is obstructed by the table on this point, so it has an opacity of 1. We will take the minimum of all of them to find that this point has an opacity of 0, which would mean that it is outside of the object. In a sense, this is similar to an older technique known as space carving, where every single point in space that can be seen by any training view directly is clearly not part of the object. You can think of this as like a sculptor chiseling away at marble and only leaving the sculpture intact. If we sample a point inside of our Gaussian, then it will have an opacity of 1, because none of the views will be able to directly observe it. It will not contribute to any of our training views. And in fact, this can even happen for points where there is no Gaussian density at all. But if it's still obscured from all the training views, then we know that this view has not been trained in any way, so it should be considered part of the object. In a sense, this is kind of casting a shadow from the views, which will be considered inside the object. Then our actual surface is going to be exactly where this opacity field will have 0.5 level set. So wherefore, one view, exactly half of the transmittance has been used up until it hits the surface. As opposed to TSDF fusion, we will not sample densely the volume, but instead we will use the Gaussians themselves as guidance as to where the density in the scene is. We will spawn 9 sample points per Gaussian, 1 in each corner and 1 in the center, and we will evaluate them for every single training view to find out if they are outside of the object, inside of the object, or near the surface. Then we can do some refinement iteration to get as close as we possibly can to that 0.5 level set of the Gaussian opacity field. And we can use a marching tetrahedral algorithm to finally extract the surface from this. Now, this is a generally good idea for larger scenes, but it can still be slow because the number of samples we need to take is equal to the number of training images we had. Then we need to sample each one of them 9 times for every single Gaussian in the scene. And if we want to do more refinement iteration, we have to do this again and again and again. So the performance of this sampling is very important. So in sorted opacity field, a kind of add-on to Gaussian opacity field, we introduced some optimization to this process, like, for example, load balancing on the GPU, not considering points that will not change the surface, potentially early stopping the computation along array, which will lead to an increased mesh performance by a factor of around 6.8. Also, we have shown that introducing some of the more accurate rendering methods that we have discussed here, like the extent loss, the exact median depth, and also the hierarchical sorting, in general also leads to a better mesh construction. So that is all we want to cover for today. Thank you for listening. Are there any more questions? Yeah?
So in terms of mesh reconstruction, how would this compare with like NURBS, this type of approach?
So in general, we have seen these explicit types of mesh extraction on certain data sets being able to beat state-of-the-art methods like News or Neural Angelo, especially with the relatively recently introduced multi-view losses.
But do you think they are going to combine? Because I think many of the realizations you do, you can better model these implicit
Yes, there very much is a way to combine those, like for example in new SG. It definitely has been done. I wouldn't currently consider it state of the art, but there's definitely room for exploration there, yes. Anything else? Yeah?
Thank you for your presentation. My question is that you mentioned that you use several filters to eliminate visual artifacts, but in most cases it costs performance. On platforms where it would be feasible, have you considered implementing some sort of obviating rendering solution? And also, would it be possible to only apply filter to specific areas?
Well, yeah, actually in the VR splitting paper, we actually also use foveated rendering to basically only render a certain part of Gaussians at full resolution. Yeah.
Thank you.
Yep.
So you mentioned you are using matching tetrahedra. Where the tetrahedra coming from? Is it developing stuff?
Yes, that is a very good question. So where do the marching tetrahedra come from? So basically when we start sampling the points, this is something I kind of glossed over a little bit, we then extract the points which are near our surface, and then we run the marching tetrahedra algorithm once to extract the isosurface as a mesh, and then for the subsequent refinement iterations, we will actually do a binary search along the normal of this mesh in order to get closer to the 0.5 level set. So essentially we have one iteration of finding a mesh using marching tets from this point and then optimizing the mesh further that we got from marching tets. Yeah.
I have a question about reconstruction. Are you handling any mixed dimensionality data? So I'm imagining for this much reader approach, you have some closed surface between inside and outside, but you might also have some non-orientable data or maybe some line structures like a piece of twine. That was in one of the examples. You might want to reconstruct differently. Is this something you or somebody else has investigated already?
Well, there is still an outside and an inside to a piece of twine, right? Mm-hmm. You just need to sample thoroughly enough.
That would be the solution currently, but that would be the result.
Yes, that is how that would currently be done. And I think if we look at the results at the very beginning, we can see that it's getting reconstructed somewhat well, I think. If not perfect. Yeah, not perfectly, but it's doable. Okay, perfect, thank you.